So very good evening, everyone, and thank you. First of all, thank you so much for registering for today's speaker series. So let me use this opportunity to give you all a quick intro about like what is DCKAP. So the community, the organization behind the speaker series. So DCKAP is a digital commerce agency and helping businesses and brands to create e-commerce storefronts. So that said, and during these challenging times and being in the lockdown, it's very much important for everyone for us to upskill and learn new things. To facilitate the learning for our employees as well as for the general community. So our DCCAP started hosting the speaker series, a virtual event, so that happens every Friday. So, through speaker series, we bring in distinguished thought leaders, technology masters, and change makers around the globe to address on varied topics, so which matters most to the community. And having said that, and today I'm very glad and proud to welcome Joish Bosco, and he's a software engineer with our community DCCAP. And I usually brag a lot of having some of the smartest colleagues around me, and George is indeed one among them, I would say. So he's experienced in Python and JavaScript, and he works in machine learning, deep learning, and computer vision. So apart from the technical stuff, he's also an excellent listener, a good speaker, and a fellow math, of course. So today he is about to speak about the true potential of the quantum computing. I hope you guys will have a great session today. And should you have any questions, feel to raise your questions in the Q&A section so that you can see in bottom of your Zoom window. And I don't want to hold you guys from the capitative session from Josh. Over to you, Josh. And thank you so much for featuring in our speaker series.
Oh, thank you, Shrija. It's actually a pleasure. It's my pleasure that I would do it here. And it's a sweet introduction of you. It's a sweet introduction. And let me share my screen first. So you guys can see. So I hope you guys can see my screen. And so first of all, thank you all. It's actually a pleasure that you guys have joined me in this week. I mean, Friday. It's actually a great day to take off. But then you guys took today and you joined here. It's actually great, and it's wonderful, I would say. So I just don't want to waste your time, and let's start into the presentation. Hope you guys can see my screen, right? Yes.
Yes, we can.
Okay, cool. That's cool. Okay. So first of all, hi. Hey, I'm Joish, as Shrija told. I'm Joish Bosco. I'm a software engineer at DCKAP. I'm working in DCKAP for the past 2 years, pretty close to 2 years as of now. And apart from being a software engineer, I actually work in research perspective of machine learning, deep learning, and to be more honest, it's more of the academic research. That's what I would usually say. So most of academic research, and today we'll be having a look at my understanding of quantum computing. Okay, so it's pretty messed up concept because it's quantum physics, right? So it's pretty messed up, but it will be fun. I'll assure you that this it's going to be fun. It will be interesting, right? So yeah. So before we go on to the screen, right? I mean, before we go on, let's start by playing a game. So it's a very simple game. It's a coin game. It's a coin game, and you're gonna play with the computer. So the computer is actually pretty simple. You have a person, and the opponent is a computer, and it's a coin game. So just a sec. So yeah, so you have two moves now. In a coin game, you actually have two moves. So you can either choose a coin. I mean, you can flip a coin or not. Okay, so initially the coin is in the head state. You can actually choose to flip a coin or not. So basically, you have a computer playing, and you are in the between. I mean, you are the man, and you actually the initially the game starts with the coin being in the head state. Okay, so the computer actually has two moves. Either you can flip the coin or not. So the computer actually does the move, and the output of the move is not actually shown to you. And yeah, so it can actually choose to flip the coin or not. Okay, so that's what is given here. Then you get your chance of either flipping the coin or not, right? So, and again the computer does it. So finally, if it turns out to be an head, the computer wins. Or if it turns out to be a tail, the you win. So the game is pretty simple. Okay, So remember this state, you're actually now playing with a normal computer. Okay. So if you play this game for n times, let's say 100 or 200 times, statistically speaking, there's a 50% chance, as you can see it here, uh, there's a 50% chance of you winning, and there's a 50% chance of computer winning. That's probability, that's statistics, and you cannot change it. And to be honest, if the coin is not biased, again, the conditions are all favorable to your situations. That's what I mean. So the coin should be in a normal state, and if the conditions are all perfect, there's a 50% chance. The odds of you winning is 50%, and the odds of computer winning is 50%. This is when you play the game with a normal computer, like a little normal computer. Consider a supercomputer also. This is what the probability is, right? So now let's go a step further and see what actually happens when you play the same game in a quantum computer. Okay, this is where things get funnier and interesting. And when I read this concept, I was like mind blown, man. Like I don't know what to do. I was actually shocked, to be honest. So what before going on to quantum computers, what actually is quantum computer is very simple. So quantum physics is actually a branch of physics which actually deals with the behavior of subatomic particles like atoms and nucleus. And quantum computer enhances or uses this quantum principles in order to work. So technically speaking, on layman's term, quantum computer enhances the principles of quantum physics. Simple, so simple, right? So so this is how a quantum computer looks, and this is actually a quantum computer built by Google. So Google actually has built this quantum computer, and it's actually released a paper. It says that it has actually met the quantum supremacy, which means when a supercomputer takes thousands of years to calculate a problem, quantum computer did it in like 2 or 3 seconds. That's very fast, and that's extremely fast when compared to a normal computer. So this is actually a computer at Google, and they're working on it. So yeah, so this is what makes quantum computers different. Yeah, so how exactly is because it actually uses quantum physics in action. So in other words, a normal computer, it's either 1 or 0. Either the computer is on, the bit is 1 or 0, whereas a quantum computer uses the properties of quantum physics in order to make it work. So that's actually interesting, and that's when you get to it, we'll see it. So when you ask me, if you compare a quantum computer to a normal computer, a normal computer is like a candle, and a quantum computer is like a light bulb. So that's the way different. So how harder you try, how much research you put into a candle, building a better candle, it's not equivalent to a light bulb. Okay, that's what I mean. So your a normal computer, you can build extremely super good candles, but it's not actually as good as a light bulb. Okay, so your normal computer is like a let's say you take in a supercomputer which is working in Google, it's actually a candle. Okay, whereas a quantum computer is like a light bulb. So that powerful is a quantum computer is. Okay, so I think this is like interesting. And let's get back to the game and see what actually happens when you play the same game with a quantum computer. Okay, the game is going to be the same, but the opponent is going to be a quantum computer than a normal computer is. So the game starts with the head state. You have two moves. Either you can flip the coin or not. The computer chooses its move, and the output of the move is not given to you, and you get the chance and you do the flipping or not, and your output is not shown to the computer. And finally, if the head comes up, the computer wins, or if the tail comes up, you win. Simple game. Okay, but now let's play the same game in a quantum computer, right? So do you guys have any idea what would happen now if you play the same computer? Because the results are very interesting for me. So I'll show you the results before we get down to the understanding. So 95 or greater than 95% of the times, the quantum computer wins easily. Just by makes it so simple. It might be like it might sound like what the hell is this? It's it might be sounding like cheating to you, but it's exactly the quantum physics in action, right? So let me show you how it works. Okay, it sounds like cheating, not exactly. It's because quantum physics in action. It is actually using enhances the properties of quantum physics, and actually sees, uses these properties to make this thing happen. So I'll show you how this actually happens. Okay, so in a normal computer, or in a normal any computer, it's actually head or tail. So you can actually have a coin in head or tail. But a quantum computer also takes into consideration the spinning state of the coin. So let's say you're tossing the coin. Okay, so the spin, when it is spinning here, it can be head and tail at the same time. Okay, quantum computer uses this property, and this property is called superposition. So this is actually a fundamental property in quantum physics. Okay, it's called superposition. So what actually happens here is it does not take the head and tail, whereas it takes head and tail at the same time. So it might be like 80% chance of being head and 20% chance of being tail. It's made 60-40, probabilistic basis. Okay, so the proportionality might be a constant, might vary a little bit, but this is what happens at the back end. So now let's play the same game in a quantum computer and see what happens. So initially the coin is in the head state. So when the coin, when you flip the coin, when the computer chooses, so what actually happens here is when the computer chooses to flip a coin, it actually puts the coin in the superposition. In other words, the coin is actually in the head and tail at the same state. So this is called the superposition, and it's actually a fundamental property in quantum physics. Okay, so whatever after it's put, after the coin is in the superposition, whatever the move you make or the computer makes, this superposition is maintained. So in other words, it's like you mixing two solutions together. Whatever you do, the solution is mixed. Okay, but in the final move, what the computer does is it actually uses a decoding algorithm and actually unmixes this mixture in a certain way that it always gets hit in always minutes. So that's what happens here in quantum physics. Okay, it actually uses a decoding algorithm where the final state is actually a win state for the quantum computer. Okay, so this is how it works. So this is actually the basic, a fundamental understanding of quantum computers. This is what the principle is. What I've told you is actually one principle of quantum computers, right? So moving further, yeah. So why go for quantum computers? Yeah, you can actually ask me this question. Okay, Joish, everything looks cool, but why do you actually go for quantum computers? We can actually do a lot of tasks with the simple computers itself. The answer is yes, but there are certain tasks where when you try executing in even a supercomputer like in Google, you might actually run out of space or memory errors will happen. So I'll give you two instances. I'll give you two instances where classical computers, even supercomputers at Google, are very bad at. Okay. The first is actually an optimizing problem. Okay. So optimizing is very simple. Let's say you have uh, 10 different ways of choosing a book. Okay. What is the best way to choose the best book? So that's actually an optimizing problem. Okay. Another example is, let's say you have a round table and you have 10 chairs and you want to make 10 people to sit in this chairs. Okay. And there are 10 different, how many combinations can you make to make these people sit? It's actually an optimizing problem, and the answer is 10 factorial, because there's 10 chairs and 10 people, so it means there is 10 factorial ways you can actually arrange the people around the chairs. Okay, it's an optimizing problem. And you can actually ask me, 10 factorial is very small. Okay, let's say you have 100 factorial. That it actually goes to a range where you actually have an optimizing problem, or it actually has a memory out of error problem. So our computers are actually not very good in solving these problems, and our computers are very bad, to be honest here. Okay, even I'm talking with respect to Google supercomputer. Okay, so the next problem is the field of chemistry. So chemistry is actually a very good field because any kind of drug development all uses chemistry. And in order to visualize a molecule or an atom, it has to, a normal computer has to calculate the bond between molecules, electron repulsion, repulsion force, and an electron nuclei attraction force, right? So it has to calculate this attraction force or bond forces in order to visualize the chemical. But let's say you have another atom come into the play, so it has to calculate all these other atoms again, which is again like exponentially harder to solve. And when you solve this problem, even a supercomputer, the maximum molecule that it can automate is actually 4 atoms, not more than that. And 4 atoms is actually very small, and we can not do any much thing with 4 atoms. Okay, so what do these problems have in common? Okay, so I told you about the optimizing problem. I told you about the field of chemistry, where it's when you try to calculate a problem, it's actually harder, right? So what do these problems have in common is the problem of exponential scaling. So one classical example of showing you exponential scaling is the chess game. Okay, so the story goes like this. So this guy invented chess, and he went to up the king, and the king was actually impressed, and he wanted to give this guy a present. Okay, so this guy asked the king, he told me, he gave the king like this way. So the first day you give me 1 grain of sand, the second day you give me 2 grains of sand, the third day you give me 4 grains of sand. 2 par 3, you say 8 grains of sand. It's exponential growth. So maybe in the end of a week, you will have a teaspoonful of rice. Whereas, in the end of 30 days or month, you will have a garage full of rice. Whereas if you go to the 64, because there's 64 blocks in a chessboard. So if you go for 64, it's actually Mount Everest size of rice. So that high rice you'll have. So that's where exponential scaling comes in, because what you can observe here is 64 is actually a small number, but 2 power 64 is actually exponentially very bigger number. And the maximum number it could solve in a supercomputer is 2 power 10 or 2 power 11. That's the maximum that could solve. And we actually have a problem, we are actually facing this problem nowadays, because our calculations exceeds this power. And what actually it happens here is, we try to approximate results here. Okay, but instead of choosing all the possible ways, we try to optimize a little bit. So let's say you have 100 ways of combining, we only given 10 ways to the computer, and the computer chooses only that out of 10 ways chooses one. Whereas there might be a potential chance where if you take 100 ways, there's a better way of getting the results. So this is the fundamental problem that we're facing in exponential scaling. Okay, so what makes quantum computer different? The first principle is superposition. Okay, so superposition is, I've already told you, it's because remember the game, right? The computer puts the coin in the superposition. It can be at the head and tail at the same time. And what I've mentioned here is actually a classical example of Schrodinger. So Schrodinger actually is a scientist, is a top scientist, a quantum physicist. So he actually came up with an experiment to prove this is correct. So what he did was, he actually took a cat, he put it inside a small box with some small poison in it, and he just closed the box. So according to his assumption, the cat is actually live and dead at the same time, inside the box, provided the box is closed. So you will never know is the cat alive or not unless the box is open. So this is what happens there in quantum physics, I mean quantum mechanics or quantum state. So this is the first principle of quantum physics. The second principle is entanglement. So entanglement is very simple. Imagine you have something in America, and imagine you have something in, let's say, India. Okay, so let's assume that these two particles, in the particle in America and the particle in India, is entangled. So in other words, just by observing the particle in America, you'll be able to figure out what is actually going out in the particle in India. So that's actually called entanglement. Okay, so this is pretty weird, because when I read it, I was like, oh, how could it be even possible? But this actually exists, and this has actually been proven by lab theories, and a lot of theories have been out, and a lot of experiments have actually proved this actually exists in the quantum state. Okay, so what happens when these quantum properties are harnessed? Okay, so first thing is quantum encryption. Okay, so everybody uses bank nowadays, right? Everybody uses online transaction, and there's a potential chance that your credentials can be hacked, because it's easy, anybody can do a man-in-the-middle attack, and it's obvious that your encryption, your key is hacked, right? But by using quantum encryption, what actually happens there, your private key is actually in a superposition. In other words, it can be in a multiple state, so that if a hacker tries to hack into your key also, it's impossible. It's actually impossible, because it's in a superposition. It can be anything at the same time, nothing. So in other words, in order to hack a system, the hacker has to break the laws of physics in order to hack the system. In other words, if you can break those laws, it's actually breaking the laws of physics, which is actually worth a Nobel Prize. That's hard, and it's impossible. And a lot of companies and banks and institutions are actually working on quantum encryption now. So you can actually see, maybe in another 15, 20 years, you'll actually have quantum encryption, and your online transactions will be way secure than the previous days. There's no way of people hacking into your accounts. So that's one potential application of quantum computing. Okay. The second the second method is effective drug discovery or medicine discovery. So I told you that it's actually hard to visualize chemicals, but quantum computing already works using the principles of quantum mechanics, and it's actually easy for the quantum computing to calculate these materials. In other words, it's actually able to visualize molecules in a better way, and we'll be able to have medicines much faster. And much faster, as in, let's say we have, like, let's in a traditional computer, it actually takes like 2 to 3 years, whereas a quantum computer would actually do it in a month. That's the span. That's a maximum span that would actually take quantum computers. So we'll be able to have much faster drug discovery and medicine discovery for even biggest diseases like Alzheimer or cancer, or maybe in COVID also. That's also possible. Okay, and the third thing is my favorite, is quantum teleportation. Okay, so you'll be able to teleport things from one place to another without even actually being teleporting the information. In other words, this is where the second principle of quantum physics comes into action. Okay, the second principle is entanglement. So what actually happens here is, you actually put the materials or the molecules or informations in an entangled state. So what you actually do here, in source A, you actually change something, and this actually changes the properties of information in source B. So which means, you're actually transporting information without physical transformation. That's what is happening there. So it's actually possible, and physicists have proven this is possible. And China has actually done an experiment. It's actually teleported a photon particle from Earth to a space station, and it's actually proven. So people are working on this, and if we have this, we'll be able to have you know broadband. We need not have any quantum. I mean, or normal internet at all. We'll be having quantum internet, and actually IBM is also working on a quantum network. It is actually trying to send information from source A to source B without physically transformed. I mean, the information being transformed through wires or wireless communications or something like. So it's actually in an entangled state. Okay, so yeah, this is again my favorite field, because I was a part of the machine learning and deep learning artificial guy. So this is actually important. So when you take any problem in artificial intelligence or machine learning, it all boils down to a factor of optimizing problem. So you take any problem in machine learning, you'll obviously find an optimizing factor where you have to reduce. But our computers are not actually very good in, it's actually good but not super good in solving optimizing problems, whereas a quantum computer can solve these problems much faster, much efficient. So you might think like a normal computer, let's say it takes 100 years to solve a problem, whereas a quantum computer can actually do it in seconds. So that's the speed ratio, and by this like a quantum computer will be able to think much faster than a normal computer would, right? So this is the field. I mean, this is what happens when you apply quantum computers to artificial intelligence. But there's also a downfall to artificial intelligence, but this point of time, anything is possible, because a supercomputer, I mean a quantum computer, would be able to think in all the possible combinations, and it can actually figure out a trigger point, which is called the doomsday. It is completely possible. Why Terminator uprising, all these things are completely possible when quantum computer comes to existing. Okay, any of you guys have any doubts with respect to this? Because basically I'm done almost like 95% of the things I'm done. So do you guys have any doubts, any questions? I'm up to answer. Any questions? Anyone?
Okay. Yeah, we do have one question, Josh.
Yeah.
So,
Yes.
question is, do we have real life examples where quantum computing is used?
Okay, so IBM has actually given you a 5 qubit quantum computer. It is actually linked to the network, and you can actually use a quantum computer just by connecting to the remote network. It's actually free, and there's, to be honest, there's 18 research papers has been published on this quantum computers. People are working on it, people are building games on it, people are working on the research perspective, and there's people from Antarctica working on these quantum computers of IBM. Okay, so they have worked on photon propulsion, and completely possible. So to answer your question, it's yes. People are using it. People are using it. I mean, people are working on it. Do you have any other questions? And to be honest, you can actually sign up for an account and use it. It's the fundamental. There's a beautiful documentation for it, and you can actually use it. Any other questions? Okay, then I think there's no more questions. So I'm just gonna. So that marks the end of my presentation, and I had a great time. Hope you guys understood some fundamentals about quantum computing, and I hope that you
I
guys
believe,
go
like,
log.
I'm sorry, Ram Alak, one of our participant needs a clarification and is
Okay,
asking again for any real example, so which is pertaining to the quantum computing at this current era or something.
I didn't get your question. Can you come again?
Any real example? He just want to know the real example for the quantum computing.
Yeah, I told you, right? 18 research papers has been published, which means people are using quantum computers to do the research work. So there is exist. I mean, people are working on the quantum computers. IBM has actually given you an access to the quantum computers. It's for free actually. You can actually log into it, and you can actually use it. And that's actually real-time proof we are working on quantum computers. But super cool quantum computers are not out. It's still under research. And when super cool quantum computer comes, you'll actually have all these things possible. Transportation, teleportation, all these things are possible, completely possible. And yeah, China has actually worked on this thing, teleportation particles. So it's again there. So real-time examples. I think that's a real-time example, right?
Asking like, so it is mostly used in research. Can you share use cases for quantum computing? Like, where can it be used in India?
Why can't we use in India? So okay, so as of now, quantum computing is the developing stages, right? So it's more of research perspective. Nobody has used it on a commercial perspective. Okay, no, because it's more of, it's in the initial stages. It's more of gating and Hermat gate and something like that. Okay, so it's not like you can actually go write programs and work with it, because writing programs, quantum computing is totally different, right? You have to consider the superposition, all those things has to come into play, which is actually different, and people are working on something called as the gate logics. Okay, so in India, I don't think we have a quantum computer, but it can actually be, I mean, banks are using it. There's institutions which has been, I know, like there's institutions which are working on quantum computers to take the classes. So that's one practical application. And banks are actually working on the quantum encryption technique. So you'll have super cool encryption so that it's impossible for people to hack your network, I mean your transactions. But
That's
in
great.
India, I have no idea.
Okay, that's great. So we have another question, and in what way will quantum computing possibly revolutionize machine learning methods?
Okay, so machine learning is a beautiful subject. Okay, so in machine learning, the ultimate problem that we have is the problem of finding the best optimizing line. Okay, a best optimizing point. So there's a lot of algorithms like stochastic gradient descent, and when you look at all these things, right, it all comes to the point of optimizing and function. A function like, let's say, x squared, or simple. I'm putting x squared because it's very simple. So in x squared, the optimal point is x when x is equal to 0, right? But consider an equation which is like 10 dimensional. Okay, like x to the power of 10 something something. So no, the way the equation itself is totally, like, it's impossible to imagine those things. Okay, so that's why you have this stochastic gradient descent and Adam optimizers all coming into the game. But what actually happens there is, our computers are not so good in calculating those things. It actually makes approximations. Gradient descent is actually called stochastic gradient descent because it is stochastic, because in other words it's probabilistic. So every time you calculate it, you might not end up with the same answer. That's why it's called stochastic. Whereas a quantum computer will actually make it stochastic more faster and more easier to calculate. Okay, so in other words, if let's say your stochastic, I mean your algorithm takes 2 to 3 years to run, whereas a quantum computer will actually do it in seconds. So you'll have extreme amount of horsepower been done there. So a lot of work can be done within a fraction of seconds. So you'll have a lot of things can be done. Like the applications of quantum computing, machine learning is to the extreme levels. Everything can be done at that point of time. Not just in machine learning, it's also in artificial intelligence as a whole. Because consider, like, when you're driving a car, right? Tesla has this algorithm for lane detection all. But Tesla doesn't have what you call it, what it cannot predict what is going to happen. Okay, but when quantum computer comes into play, it can actually make sure that it can predict what is going to happen. In other words, it will actually calculate all the considerations, all the parameters of the environment of the game. It can figure out, is this person going to cross the road or not? If it crosses, what will happen? If it doesn't cross, what will happen? So Tesla doesn't work on these cases. But if a quantum computer exists, we'll actually have situations where this is possible, and we'll actually live in a world where AI will rule us. That kind of world is possible, completely possible.
So that's amazing, Josh. Like, we even couldn't believe our eyes on the coin tossing game, like which you explained, and the transportation. So if it comes in live, it's going to be really cool if that transportation comes. So thank you so much, Josh, for your valuable time, and it's kind of in fun learning the quantum computing. So let's see, like, how it takes us in the future, and how it is commercially used, and etc., all other stuffs. And thank you so much for the insights for this evening. And before ending this session, like, I would like to give an intro for the next session, which is on the June 5 on Friday. So let's see, like, who is in the line and who is the presenter for the speaker series. So we have Manish Nepal, and he's a content marketing specialist and podcaster in ABM conversations, and he have like 10 years of experience in content marketing strategies. And I believe this is a good session for the salespeople and the marketing people and who work in B2B. And he's gonna have a conversation about organic content marketing and strategy for better conversion with $0 ad spends. So it's kind of a tricky topic as well. So let's see like what we have, what he has for her in the conversation. And that said, like, thank you so much everyone for your valuable time on this Friday evening, and happy weekend, and see you all in the next speaker series. Thank you so much. And at last, thank you so much, Josh, for the insightful session. Thank you.